Hello, everybody. Come on in. Come on in, everyone. Feel free to ask any questions you might have. I'm getting ready to do a really ugly surface integral problem. So that'll excite you, I'm sure. Just to give you an idea how, quote unquote, a surface integral is to be done. Your book has a couple of them. And in most cases, you can almost always make it a little simpler just by doing certain things. So hopefully you can pick those out, and I'll let you see sort of where that goes here. So anybody have any questions while we're waiting for people to straggle in? I don't see any coming up on the chat yet. I still see more people coming in. We got 8 students plus me in here right now. That's not too bad. I've got my cool Mandalorian picture up there, which I think is absolutely necessary. So also with my cool nebula shower curtain that separates me from the outside world. And that right there is my violin, which you can imagine I'm a freaking awesome violinist. Nope, I was horrible at that. Switched to banjo. I was pretty decent at that, but a friend told me you start a banjo, first thing you lose is your friends and then your teeth. So that wasn't too happy, and my wife didn't like the sound of it. Now I'm playing the guitar, and I'm pretty much equally bad at all instruments. Anyways, just waiting for people to come in. Doesn't look like we have any more rapidly coming in, so I guess I should go ahead and get started. So what I'm going to do is we started on Gauss's law, and I'm going to post some more videos on Gauss's law. If you subscribe to my YouTube channel, you should have gotten several notifications. I think I posted 4 or 5 different videos this week. I've actually written up about 12. It's just a matter of me taking, in some cases, I've taken the actual video and rendering it properly to put on YouTube. In other cases, it's me where I've actually worked the problem. I just have to film it and then do the rendering and then posting on YouTube. So I've got a lot of problems in the queue that should be coming up probably today. Maybe tonight I might get a couple more, and then tomorrow I might get 1 more, and then Thursday I have a long day where I can get a lot more done. So hopefully that'll come up, and it'll be more Gauss's law type problems and ones that are more robust. In other words, some of them where you're actually going to do an integral, but on the right hand side. As I told you before, when you're using Gauss's law the way that I've taught you so far, which is using Gauss's law in integral form to extract the electric field by means of a wise hypothesis and use of a wise Gaussian surface, you can extract the magnitude of the electric field out of the left-hand side of the equation. Once you work out the left-hand side and the right-hand side, sandwich them together, and then solve for E. That is the main thing we're doing right now with Gauss's law. And I'm going to show you some of those, but I'm going to make it a little more complicated by letting the Q be, instead of uniformly distributed, maybe I'll make it where it depends on R or R squared or something like that. So just to give you a little bit more flavor of how you can change it up and give you a lot more examples to solve. So before I jump into that, any questions? Giving you one last chance to ask questions before we jump in. Okay, so it looks like nothing in the chat. I'm assuming we'll get a bunch of people coming in and out as class goes, so I'll try to let them in as soon as I see them. I'm going to start by sharing up. I'm going to start by sharing my open notes iPad screen, and you should see that I have a 3-dimensional coordinate system drawn up here. Notice it is what we call a right-handed coordinate system. Again, take your right hand to make it in that shape. It's got to be your right hand, not your left hand. Your index finger points, that's your index finger, points in the direction of the positive x-axis. Your middle finger points in the direction of positive y-axis, then automatically your thumb will point in the positive z-axis. And in this case, the x-axis is pointing out of the board, The y-axis is pointing this way, the z-axis is pointing up. So I know it's a right-handed coordinate system, and we're all very, very excited about that. Now what I'm going to do is take a very simple shape. I'm going to take a shape that will be, let's say, a rectangular solid. And this rectangular solid is going to be 1 meter high. In other words, parallel to the z-axis is going to be 1 meter. Parallel to the y-axis is going to be 3 meters. So this is what the box is going to look like. The back surface of the box, that is. And then the front is actually going to protrude out a distance of 2 meters, which I'm going to say is roughly here. And then again, I'm going to say, whoa. That didn't turn out so well at all. I'll do like that. That looks pretty good. I'll draw like this. That looks pretty good. Like this. Like this. Like this and that. So that's supposed to be our rectangular solid. I will mark it as a rectangular solid by mentioning that this is 3.0 meters. In other words, our x, y, and z axes are measured in meters. This one, which is a little cattywampus and it makes me a little angry to see, is 2.0 meters. And this one is 1.0 meters, like that. And I'm going to define my electric field in a very special way. The electric field, remember I told you a field is basically anytime you assign a particular quantity to every point x, y, z in space. Okay, so what I'm doing is I'm doing that now, and I'm defining it so that it works out kind of nicely. I'm trying not to generate a flux that gives me bigger than 0, because a flux that gives me bigger or smaller than 0 means I've created an electric field that forced a charge to be inside, because Gauss's law says that the integral over any closed surface is equal to the charge enclosed divided by epsilon naught. I'm trying to avoid that. So in principle, it could be a function of x, y, and z. That's why I wrote that. And then I'm going to say it's actually 2.0 times 10 to the third newtons per coulomb I hat plus 2.0 times 10 to the third newtons per coulomb meter squared x squared j hat. Notice the x is going to come out in meters, so that's got to cancel out with that meter squared in the bottom. And then I have z term, which is 4.0 times 10 to the third newtons per coulomb meter squared again in the bottom to account for this y squared, which is a k hat direction there. And that's sort of what you have to do. That's basically like a typical electric field. Now, I can't tell you how bad this my OCD is bothering me right now with this crappy looking rectangle. So I am now officially succumbing to my mental illness, and I would like you all to bear with me for just a second. So yes, it really is this bad. Okay, so this is going to go this way. This is going to go that. Yeah, now that just made it worse. Now I'm really angry. Okay. Okay, you stop correcting me. How about that? So we'll say this goes this way. This goes this way. This obviously went that way. This goes straight down to here. This is going to go straight over to here. That's going to go straight over to here. I'm going to get rid of you completely, but oops, that is not erasing. Get rid of you completely. That's what get rid of you too. This here and that here, and I'm sorry that you had to see that, but this is the life I lead, and that moderately makes me feel a little bit better. Now, here's the trick with a surface integral. So Gauss's law, which involves a surface integral, says the closed integral of E dotted with dA, and that circle around the integral is just to indicate, hey, don't do this problem unless you're taking a surface integral over a closed surface, meaning a surface that has a clear inside and outside, like this rectangular shape does. This rectangular shape, if you had something quote unquote in the box and you wanted to take it out of the box, the only way you could do so is to go through one of the 6 border walls. That makes it a clear closed surface. But Gauss's law says if you have a closed surface, then the total flux through that surface is equal to the charge enclosed divided by epsilon naught. So I tried to create an electric field that wouldn't be so radical that it would actually force us to conclude there's a charge in it, even though I didn't draw one. So the other thing is when you're doing a nasty looking integral symbol or something like that, like this closed integral at E dot dA, you've got to remember that this is called a surface integral, and you have to evaluate the integrand, which is both the E and the dot dA on each surface as you integrate that surface over that surface. So for instance, if the electric field had a Z value with the K component, then on that top surface, Z is equal to 1. I would have to replace the Z in that third component. And I only have to do that third component because remember, it's going to be a dot product with the A vector, the dA vector. The dA vector for that top surface is going to point up, which is in the K direction. So only that one's going to matter on that top surface. But if it had a Z dependence, then I would have to write that Z equals 1.00 meters. So I would have 4.0 times 10 to the third newtons per coulomb meter cubed times times Z times Y squared. I would actually substitute 1 meter in for Z. And similarly, when I did the bottom surface, I would substitute 0 meters in. Okay, so that's what I mean by saying it's a surface integral and you have to evaluate everything on the surface. So what I normally do is I first label my surfaces, surface 1, surface 2, surface 3, and then I go through and write down the critical conditions about it. So this front surface is 1. This side surface is going to be 2. This top surface is going to be 3. I'm trying to write the numbers even in an angle where it looks like I'm doing what I'm supposed to be doing. Next, I'm going to go to number 4, which I'm just going to basically start with the opposite. So the opposite side of number 1 is going to be number 4. So I will write that like this. So you can see that it's a number 4, but that it's in fact written on the other side. Okay. And then opposite number 2 would be number 5, which I'm going to write like this. And then opposite number 3 is going to be number 6, and I'm going to write that like this. So we now see what each of our surfaces are: 1, 2, 3, 4, 5, 6. Now I'm going to write down the conditions. This is where you write down basically, hey, what is dA for that surface? Or hey, what is X? What is Y? What is Z? So for instance, let's write them down. I'm going to switch to, I think I'll switch to blue and keep that color now. Actually, maybe I'll do a darker blue. So surface number 1. That is a really dark blue that I did not mean, but I guess that would be good enough. Okay, so surface number 1, we have that in fact, if I hadn't erased so much of this, it'd be a little bit more obvious. But on surface number 1, we can see that X is equal to 2.0 meters. Okay, I also see that on surface number 1, the Y goes from 0 to 3. And the Z goes from 0 to 1. And finally, dA is going to be, now when I look at this, I realize the only part of the electric field that's going to matter here is the I hat component. And the I hat component in this case does not have any variables in it. So I can make the integrand narrow in one part and wide in the other part, and it doesn't matter which one. So what I'm going to do is I'm going to say dA is actually equal to, since it's 1 meter tall, I'll say 1.0 meters dx I hat. That's supposed to be an I hat, like that. Let me write that below because that got way too small. Actually, we'll just do this. Make this a little smaller too, and that'll help. Okay, so Z goes from 0 to 1. And now dA sub 1 is actually going to be 1.0 meters, because that's how tall it is, times d, let me see, I am integrating, oh, it's dy, not dx, sorry about that, times dy, and that points in the I hat direction. Okay, so what I'm looking at as my differential area element is a differential change in y, and it should actually look something like this. Notice the height of that is 1 meter, and that distance is dy. Now for part two, we have y is equal to 3.0 meters. Okay. We have that x is going to go from 0 to 2. And again, that's meters. I'm just leaving it off. And z is going to go from 0 to 1. And in fact, in this case, since the dA vector has to point in the j hat direction, only the middle term is going, only the middle term of the electric field is going to matter. And that one has an x squared dependence. So I got to make sure that my differential area element, my dA, doesn't change more than infinitesimally from one part to the next over x. So this forces, unlike the other one, I had some freedom. This actually forces my dA to be this, where this little distance right here is dx. So my dA2 is going to be, again, 1.0 meters dx, and this time it'll be j hat instead of I hat. Okay. Again, I'm not quite happy with that. I wish I would have written it bigger, but it fits. I guess it's all right. Okay, and I'm going to do the same thing with this, make this just a little neater. So the dA2 is supposed to be, well, this is not good. It keeps erasing everything. Well, let me go ahead and erase everything then. All right. So dA2 is supposed to be 1.0 meters times dx pointing in the j hat direction. So hopefully y'all can see that now. Of course, when you get it, you can always expand it, but that's basically what the surface 2 has. Now surface 3, which is the top one, that has obviously z equal to 1. Of course, it has x going from 0 to 2. And it has y going from 0 to 3. So dA3, in this case, only the k hat's going to matter, and the k hat has a y dependence, so I got to make it infinitesimally small in the y direction, which in fact forces our differential area element to be like this. Now, it doesn't force it to be like this. For instance, if you were doing double integrals, you could call it dx, or excuse me, yeah, you could call it dx dy, and that would be fine. But we're trying to use single integrals, so I have to do it this way. And this width right here, of course, is dy. So this will be the whole length, which is 2.0. So let's zoom in again. This will be 2.0 meters dy, and then that's going to point in the k hat direction.
Excuse me.
Yes.
How'd you get the 2.0 meters?
Okay. The distance of the length of that rectangle I just drew went from the YZ plane out to, or excuse me, the YZ plane out to x equals 2. So that distance would be 2 meters minus 0 meters.
Okay.
Does that make sense?
Yeah.
Okay. I'm going to make that a little better. That looks a little better anyways. Okay. So now I can give myself a little bit more room because the picture's getting out of my way a little bit. I'm going to go ahead and do number 4. So surface number 4, which you see is the back surface, surface number 4 has in fact x equal to 0. So if one of these components of the electric field had an x in it, I'd have to substitute a 0 there. Now the y is going to go from 0 to 3. And the z is going to go from 0 to 1. And dA4 is going to be the exact same thing as dA1, except with a negative. So we're going to write equals negative. We can look back at this. We can see that's 1.0 meters. So I'll say 1.0 meters, and then dy, and then I hat. So that allowed me to open up quite a bit more just by writing it that way. Okay. Surface number 5, which is the opposite of 2. So it's going to look mostly like 2. But in this case, the actual y value is equal to 0. The x is going to go from 0 to 2. And the z is going to go from 0 to 1. And the dA5 vector is also going to point in the negative direction. So let's put a negative. And notice it's a j hat, so the x has to be finite again. So I'm literally going to use the exact same dA as I did for dA2, only now I'm going to do it with a negative j hat instead of a positive j hat. So that answer becomes negative 1.0 meters dx j hat. And then finally, 6 surface is in fact the opposite of 3, which is the bottom. That gives me z equals 0. X is going to range from 0 to 2. And by the way, these ranges come in handy when you integrate, because you got to integrate over the whole surface. So if you're integrating over x, you can just look, oh, this is surface 5. So integrating over x means I integrate from x equals 0 to 2. That's why I do that part. Now the y is going to integrate over or go from 0 to 3. So the y is going to go from 0 to 3. I'll put 0 to 3, and then dA6 is going to be again negative, but this time it's the same thing as the negative of 3, but it's going to be negative 2.0 meters times dy times k hat. Okay. So really, when I go to calculate the electric flux, which you all know is given by sort of the green lantern symbol, It's actually the Greek letter, the case Greek letter phi. Okay. And I've got to integrate this over each of the surfaces. So in surface 1, I'm going to take my I hat component, which by the way does not have any whatsoever functional components. It's just a constant. So I'm going to call this 2.0 kilonewtons instead of 10 to the third per coulomb I hat dotted with 1.0 meters dy I hat. Okay, that's over surface 1, and since I'm integrating over y, I got to integrate from 0 to 3. Plus, now I have another integral. This time, the only one that survives, since I'm doing surface 2, the only one that survives is the j hat. So I'm going to call this 2.0 kilonewtons per centimeter squared times x squared j hat dotted with, now I've got to take my dA, which would be 1.0 meters dx j hat. And now I get to do my third integral. Oh, by the way, the x is going to integrate from 0 to 2. This one was y equals 0 to 3. Okay, so now I've got to have my k component, which is 4.0. And this again would be kilonewtons per coulomb meter squared. The dependence is y squared. It's going to point in the k hat direction, and it's going to be dotted with 2.0 meters dy k hat. Very, very small. Let me show you what it is. Again, when you get the actual document, you can look at it again. This is the actual dot product right there. That's 2.0 meters dy k hat times that. The main thing that you're trying to see here is that, remember, I've told you over and over again, the dot product is a linear operator. So in this first integral, the 1.0 meters times dy, I can pull that completely out in front of the other I because it's just linear. And not only that, the 2.0 kilonewtons per coulomb, that's just a constant too. So if I multiply 2.0 kilonewtons per coulomb times 1.0 meters, I'm just going to get 2.0 kilonewton meters per coulomb. So ultimately what I'm going to have here using red is 2.0 kilonewton per coulomb times a meter times the integral of, notice how everything's out except for dy, I hat dot I hat was just equal to 1, and this is an integral from 0 to 3. So basically that's going to give you 3 meters times all that. So I get like 6 kilonewton meter squared per coulomb. Something similar will happen to all this. I'm going to get 2.0 kilonewton. Notice I had a coulomb per meter squared in the bottom. That's going to get rid of one of those because I have that 1.0 meters. So that's going to be coulomb meter. Now I'll have the integral of x squared dx. And that's from x equals 0 to 2. And remember the j hat dot j hat was 0, so that gave all that. And then this guy over here is going to be 4 times 2, so that'll be 8.0. It was 2 meters, so it's going to get rid of one of the meters in the bottom, so it's kilonewtons per coulomb meter. But I have a y squared dy, so I'm going to integrate from y equals 0 to, oh, I didn't write that before, but y equals 0 to 3. And that integral will be y squared dy. Again, k hat dot k hat was 1, so we're done with that. Okay. So that's sort of the quick and easy of how we do that integral. That's just the first 3 surfaces. The next 3 are done the same way, but you can probably see what's going to happen. I'm going to get the integral from 0 to 2 of 2.0 kilonewtons per coulomb I hat dotted with negative 1.0 meters dy I hat again, plus integral from, and this was from x, ooh, that was supposed to be a dy, excuse me. So that's from y equals 0 to 3, actually, not 2. So I'm doing number 4. Right. Now number 5, I'm doing x equals 0 to 2. Again, the exact same function, 2.0 kilonewtons per coulomb meters squared x squared j hat dotted with negative 1.0 meters dx j hat plus, again, integral in this case from y, in this case from y equals 0 to 3 of 4.0 kilonewtons per coulomb meter. Oh, this should be 8. Well, I'll just leave that. Coulombs per meter squared. K hat. Oh, left off the y. Y squared. K hat dotted with negative 2.0 meters dy with a k hat in there as well. Okay. I think you can look at that and see that ultimately we are going to get this first integral, the very first one that I've got the red underline, that's going to become the integral of dy just becomes y. So I'm going to get 3 meters minus 0 meters. That's going to in fact give me 3 times 2, which is 6.0 kilonewton meters squared per coulomb. The next one is going to be 2. I've already done the 1, but in this case, I'm going to integrate x squared. So that's going to become 1/3 x cubed, which will be 1/3 of 2 times 2 times 2, which is 8. So 8 times 16, or 8 times 2 makes 16. And then I divide that by 3 and I get 5 1/3. So this will be plus 5.33 if I want to carry an extra digit, and that unit comes out to be kilonewtons meters squared per coulomb, and that's for the second one. And then the third one becomes 4 times 2. That actually gets me coulombs per meter, and then when I integrate that, that becomes meters cubed on top. So I'm going to get kilonewton meters squared over coulombs again. So this will be 8.0 kilonewton meters squared per coulomb. Oh, and I forgot to, the 8 was already there. I forgot to integrate y squared. So let me not jump into writing that as 8 yet. So I had an 8, 4.0 times 2 is 8, but now I'm integrating y squared from 0 to 3. So that'll be 1/3 y cubed. So I'll take y, I'll take 3 times 3 times 3, which is 27. Then I'll divide that by 3, which is 9. So I got 9 times 8. This will be 72 instead of what I said before. 72.0 kilonewtons per kilonewton meter squared per coulomb. I can go ahead and do number 4. I think you can see what's going to happen with number 4, which is the first one on the second line. I get a -2, or basically a 2 kilonewtons per coulomb times a 1, -1 meter gives me a -2. And then I integrate from 0 to 3. That's going to give me a 3. So 3 times -2 gives me -6, -6.0 kilonewton meters squared per coulomb. Now I'm going to go to number 5. I get again 2 times -1 gives me a -1, but then I have an integral of x squared from 0 to 2. The integral of x squared is 1/3 x squared, or 1/3 x cubed. So 2 times 2 times 2 is 8. 8 times -2 would be -16. I divide that by 3. I get -5.33. Again, that's kilonewtons meters squared per coulomb. And I know, guys, this ain't any more exciting for you than it is for me. But I just show you once and for all, and you'll see all these different details that go into this when you go to do a problem. And if you look in the back of your book, I think problem 9 of the 4th edition had one, and problem 61 of the 4th edition had one. So you'll find a couple of them in there. You'll run into them, in fact, in your practice test, which I haven't put up yet. So this shows you all the bits and pieces, and by seeing all the bits and pieces, you can sort of look ahead and say, well, I don't have to do that one because obviously the z is going to be 0 there and stuff like that. So let me do this last one. I get 4 times -2 be -8, and then I'm going to get 1/3 y cubed evaluated from 3 to 0. So you might as well say that's 9 times -8, which would be -72. So I get plus -72.0 kilonewton meters squared per coulomb. I don't like how that 0 turned out. It looked too much like a 6 in my writing. So I'm going to change that to a 0. And this is a kilonewton per meter squared, or excuse me, kilonewton meter squared per coulomb. So you ultimately see that the flux is 0, which is what we expected because there was no charge in there. And I specifically tried to make an electric field that would not look like a charge was in there. So that's a big nasty, that's a big ugly, that's the last most gross calculation you'll have to do this semester. It's not that hard. It's just a piece by piece. In the words of Julius Caesar, divide and conquer. So that's all you do is you look at the symbol, try to make sense of what the symbol means. I see an integral E dot dA. That means I have an electric field that's taking a dot product with a dA vector. That means I got to figure out what the electric field is. I got to figure out what dA is. I know how to define dA, but I also have to be careful with dA since I'm only want to do single integrals. I want to only have a, sort of like when you tried to determine the volume of a sphere, you used washers, or if you want to try to find the volume of a hollow cylinder, or excuse me, you use discs. But if you want to find the volume of a hollow cylinder, you use washers. Those were all neat little tricks that you used in calculus to try to do a single integral. If you actually did a double integral to calculate an area, it'd be a lot easier, and you more or less have no integrand other than what you're calling dA or dV or whatever. If you're trying to calculate a volume, you're actually going to have a differential volume element and no integrand with that. So it's a lot easier to do multiple integrals. In this case, we're forcing ourselves to do single integrals because you guys aren't required to know multiple integrals yet. So you just got to be very careful. One, in making your functions. That's why I had to make sure I didn't have like a x squared y in one of the terms, because that would mean both x and y had to have infinitesimally narrow differential areas, or else I'd have to find some averaging process. So I just didn't want to do that. So That is a surface integral. That's how you go about doing it. Notice I just took one side at a time. I realized that the dot product was only going to pick out the components of E that were parallel to the dA vector for that particular side. That's why I didn't have to worry about, for instance, side or component, the J hat component, when I was doing face 1, nor when I was doing face 4. That's why I didn't have to worry about the first and third component when I was doing face 2 and 5, because the third component points in the K direction, and face 3 and 5, or excuse me, 2 and 5 point in the J and negative J direction. So any questions on that? All right, so that's just a really good intro. Now I say good sparingly, but I'm just trying to say that is a robust example of doing a surface integral. And that's really, if you maybe had taken a calculus class at one of the huge, most prestigious universities in the world or in the United States, like Princeton or MIT, where literally every student came in having already completed calculus, literally almost every student having already completed calculus 1, 2, and 3. Then sometimes they can go a lot further in Calc 3, and you would actually cover, probably, you might not get the surface integrals, but you definitely get to some vector calculus. So, but don't feel bad. I didn't get to go to one of those places. I got to go to a community college as well. So it's definitely not an insult. It's awesome. I saved a ton of money. My daughter did the same thing. She could have went other places. She went to a community college as well. So don't ever look down on yourself because of that, because we deliver the goods. We have to, by law, have our students, when they transfer, do just as well, if not better, than the students that started at that university. So our GPAs at the end of our third year for transfer students from TCC to, say, JMU or UVA or Virginia Tech or ODU or Hampton or Norfolk, our GPAs for RTC students that did their first 2 years at TCC and then did their third year and their fourth year at JMU, NCSU, Hampton State, or UVA or Virginia Tech, their GPAs are better. So, we're doing right. Okay. So again, one more chance. Anybody have any questions on this god awful, satanic looking problem that's clearly somebody's going to get us for having written such chicken scratch on this board? I apologize about how small I got. Remember, when you're looking at the document, you can always zoom in. That'll help you. Apologize that it got that tight like that. I didn't want it to, but all right, so that's it. All right, so what I want to do now is another really good Gauss's law problem. The first thing I did was a spherical Gauss's law, where I actually treated a sphere that was not a conductor, because a conductor has this neat property that electrons are free to move around throughout the conductor. So for instance, if you make a bar of aluminum or a sphere of aluminum, any free electrons running around in there that aren't, so attracted to the atom they're next to, they're just going to be running all around wherever they want. And ultimately, because there's many of them in there, they're going to try to get as far apart from each other as possible. And what ends up happening is, on a metal that doesn't have, for instance, a battery connected to it to power it, but on a metal, once it's charged, or even before it's charged, the free electrons are going to tend to get themselves as far away from each other as possible, and they'll actually orient themselves over the outside surface. And they're then becoming what we call a surface charge, which we had been indicating by the symbol sigma, which is literally the number of charges in coulombs divided by a small area, small enough so that when you got from one part to another, it always gave you the same result. Okay, that's what we'd call a uniformly distributed surface charge, sigma. So we did a non-conducting one, in which basically every cubic centimeter or every cubic millimeter or every cubic inch, whatever you want it to do, if you pulled it out of that material, found out by whatever means how much charge is on it, divided that charge by the volume, you would find, as long as you were using the same units, the coulombs per unit volume were exactly the same for every other chunk of that conductor that you worked with. So if you took one that was inch by inch by inch and you divided the total charge by the cubic inches and then converted the cubic inches to cubic millimeters, you would get a number that happened to be exactly the same number as you got when you did a single cubic millimeter, determined its charge and divided that by 1 cubic millimeter. Okay, that's what uniformly distributed charge means. And in fact, we usually indicate in a couple of different ways. We could say, for instance, that lambda, and I'm going to go back to my blue. We could say, for instance, that lambda is sort of defined to be dq over dl. Okay, now lambda doesn't have to be a constant, but if it's uniformly distributed, then yeah, lambda is a constant. Another one we have is sigma, which is that symbol there, and that's actually dq over dA, where A is an area element. That bottom, that dA in the bottom, which is a whole mathematical thing all by itself, is not just part of a symbol. That dA in the bottom would have units of square meters. And then also, if you're talking in 3 dimensions, so charge could be distributed through all 3 dimensions, in which case it'd be dq over dv, and that dv would have units of cubic meters. I don't like expressing it that way because it gives you some idea that you've got some q as a function of x, y, and z, which I've never ran across in any of my labs or anything like that. So I like to actually put it the other way. And what I would say is the equivalent is that the charge q, it can be either equal to the integral of lambda dl, or it can be equal to the integral of sigma dA, or it can be equal to the integral of rho dv. Whoa, I didn't do so good on that dv. Okay, that's the way I prefer to use it. And in fact, when we're dealing with Gauss's law, the closed integral of E dot dA is equal to Q enclosed over epsilon naught. That Q enclosed can actually be given by these things. Okay, that's just another level of complexity we could bring to the table if we so desired. And that's what I did with the very first one. Remember, the very first one, I did a solid non-conducting cylinder, or excuse me, sphere, whose charge was distributed uniformly throughout it. And therefore, I calculated the electric field everywhere. And when I did on the inside, the only part that mattered was the Gaussian surface, or the charge within the Gaussian surface, which happened to have a radius r, which was less than the radius of the sphere, which was big R. And that's because I wanted to know the electric field at the radius little r. Okay, so that's what we did with that. That's how that works. Now, one thing I did do was, in fact, a infinite line charge. I mean an infinite charge surface. So I'm going to do one of those, and then I'm going to try to fit in basically an infinitely long cylinder. So you'd see the 3 symmetries. So let's start off with drawing a little coordinate system. Okay, and this is, again, where I make use of coordinate systems that exist in mathematics, not because I want to throw you off or make your life difficult or anything like that, but just because we can borrow from it some very, very, very helpful symbols. Well, we can borrow from it some very, very helpful symbols. And because we know what those symbols are, I don't have to stop and explain them every time. So that's why I do it. So there's my x-axis, there's my y-axis, and there's my z-axis. And what I'm going to use here, even though I'm doing an infinitely large plane, I am going to use a cylindrical surface, and I am going to make use of cylindrical coordinates. So I'm going to go ahead and draw my plane. And in this case, I'm going to draw my plane to be in a beautiful greenish color. Okay. And in fact, it's an infinite plane. I'm very specifically trying to draw just a small part of it, but I want to remind you that it goes on for infinity that way and that way. And it goes on for infinity that way and that way. Okay. And I want to remind you that it has a uniform charge density sigma. So in this example, plane is infinite and charge is uniformly distributed. Which means sigma equals a constant. Now, because sigma equals a constant, and because of the bigness of this plane, you should be able to reach the conclusion that the electric field for this, at least above the plane, which is literally the plane's lying in the XY plane, but the electric field above the plane should point exactly upward. In other words, if you think it had a little bit of an X component because of some little X charge over here, remember there is diametrically opposed equal amount of X charge right over here that would counteract that and set it up properly. So you don't have to think about that. And in fact, that's part of our hypothesis, is that when I go to hypothesize what the electric field is going to be shaped like, I'm going to assume that in fact it only has a Z component, and in fact the Z component only, or the magnitude of it only depends on the distance Z that it is from the nearest point on the plane. So as you can tell, my OCD has gotten the best of me. I'm trying to fix my drawing again, but here I am. Luckily this time I didn't do it in such a way that it made everything bad. Okay, so I want to know what is the electric field everywhere. So that's my big question. All right. Now, my hypothesis is that E is going to be a piecewise function, E that only depends on Z, E of Z, and points in the k-hat direction for Z greater than 0, and it's going to be the exact same function, E of Z, multiplied by negative k-hat for Z less than 0. So there's my hypothesis. All right. Now, given that that symmetry of this infinitely large plane dictates that kind of electric field, then I suspect I need to find a Gaussian surface that is everywhere, either has a dA vector parallel to E, which, by the way, happens to force the electric field to be constant on the plane represented by that dA vector, or 2, that happens to be perpendicular to the dA vector. So y'all might want to look at this and start thinking, what kind of shape has one side whose dA vector would be exactly parallel to the electric field, and then has maybe another side whose electric field, or excuse me, whose dA vector would actually be perpendicular to the electric field. See if y'all can think up that, and I'm going to go ahead and just take the time to draw the actual Gaussian surface that I desire. Okay, so that's my Gaussian surface. If you were to think about this in cylindrical coordinates, which is a really nice way of thinking about it, then you could imagine a line that points from the z-axis to anywhere on the top edge of the circle is what we call an R or a rho, depending on what books you're using. But one of the coordinates of cylindrical coordinates is how far away, using only X and Y, ignoring Z, how far away is a point from the Z-axis. In other words, if you took the X and Y that the point had and you squared the X and you squared the Y and you added them together and took the square root, you'd get the quantity rho. And that would be one of the variables that you use to locate a point in cylindrical space. I just drew a line pointing out the rho. Now that line, if we imagine our z-axis teleported up to up here, you'd see that that line actually makes an angle theta with the positive x-axis, and that's exactly the theta that we use in cylindrical coordinates. Now, if you allowed that line to wiggle just a little bit by going from theta to theta plus d theta, then you get another wonderful little line that points out again to a different spot on the edge of the circle. And now you have a piece of pie, okay? That, notice it's shaped just like a piece of pie. Now, if you considered a very specific rho value out from the z-axis, and you held that rho value constant, it would make this little shape right here, okay? And that distance would be rho. Now, if you allowed rho to vary from rho to rho plus d rho, it would make, and I'm not drawing it perfectly, but I'm doing pretty good, it would make another slice just like that. And if you took the time to look at that, what you'd see is it looked like this. And this distance from here to here is a distance d rho. And this distance, this arc distance, by the way, is r d theta, or excuse me, is rho d theta. So we know the area would just be rho d theta, but since I have two d's, that would require a double integral. We don't need to do that, but I'm just trying to show you how this actually gives us a nice little dA that I'm never going to use, because like I told you, if you're using Gauss's law and you do the left-hand side, the closed integral at E dot dA, and you're actually having to compute an integral or fill in stuff about the dA vector more than just dA k hat, you've done something horribly wrong. I just wanted you to know that, in fact, it does have something. So the dA vector for the top, I'm just going to call dA sub t is just dA, and it points in the k hat direction, because lo and behold, the third coordinate in polar coordinates is just the z. So obviously the k hat vector comes with it. You could also probably figure out that the theta hat direction is just perpendicular to the rho hat direction. The rho hat direction, by the way, would just be that direction, and then the theta hat direction, at least for this particular part, would be that. So you can see the theta hat and the rho hat actually are just x and y type vectors. They lie in the xy plane, or parallel to the xy plane. And in fact, if you really wanted to know the details, rho hat rho hat is equal to cosine theta I hat plus sine theta j hat j hat. And you can calculate the magnitude to see that it is in fact the unit vector. The theta hat turns out to be negative sine theta I hat plus cosine theta j hat. Okay, so that's really what they are. You don't need to know any of that stuff. All you need to know is, hey, when Mr. Younger points a vector upward, parallel to the z-axis, he's going to call that the k hat direction. If Mr. Younger points a vector parallel to the xy plane, but pointing radially outward from the z-axis, he's going to call that a rho hat, or he might slip up and call it an r hat sometime. So if you look over here, there's in fact another neat little thing we can do just to, again, see what it is. Let's say this spot right here and here. Okay, what I've done is, again, I've allowed us to go out to a distance, this time not rho, but r, where r is the actual radius, if you will, of that cylinder. And then I let another one go out at a height, instead of being z, at a height of z plus dz. And then I did another one here after allowing that first one to move through an angle d theta. And that's given me yet another patch. That particular patch, which would look like this, has a height dz and has a width rho d theta. And that, of course, has a unit vector that points radially outward from the z-axis, but with no y component. And that is, in fact, my dA soup label is what I call it, but it's also parallel to the rho hat vector. Okay, so now we know what we need to know. So for the top, we've got dA top is equal to dA k hat. For the soup label, again, we're thinking a soup can here, and you're thinking of a cylindrical soup can. And if you sliced vertically straight down the edge of that soup can, you would allow that soup label to break off. And if you could, shimmy off the label with the glue coming off so that it don't rip it all to shreds, it would lay out flat into a rectangle. The height of the rectangle would be the height of the can, or at least the height of the label part of the can. And the length of the rectangle would be 2 pi times the radius of the can. So that's what we're talking about here. So the soup label has a dA given by dA soup label is just going to be, notice I don't put in, I told you what those things are. I told you they were all rho d theta, or I told you they were rho d theta d rho, stuff like that, but you don't really have to use them. But what you do use is rho hat, and then of course the dA for the bottom. That's the same thing as a dA for the top, but it points down. So I'll write dA k hat with a negative symbol in front of it. So now I'm free to take my left-hand side. So here's the left-hand side of Gauss's law. Remember, this is Gauss's law right here. This part's what I'm calling the left-hand side, and this part's what I'm calling the right-hand side. So that's what I mean. So the closed integral of E dot dA is equal to the integral over the top is just going to be E of Z, using a very specific Z, specifically the Z at the top of the can. So the E of Z is truly a constant. It's E evaluated at the height of the top of the can, and it points in the positive k hat direction because the top is for Z greater than 0, and that's dotted with dA k hat. So in fact, the linearity of the dot product means the dA can come in front of that k hat, and I get k hat dot k hat, which is just 1. And then I have plus. Here I'm going to write the plus or minus E of Z K hat dotted with dA rho hat. Now, this is for the soup label portion. Does anybody understand why I put plus or minus in that integrand?
Because it's above and below the plane.
Exactly. So when I'd have to integrate from, say, -4 centimeters if the can was 8 centimeters tall, I'd have to integrate from -4 centimeters to 0 using the negative sign. And then I'd integrate from 0 to +4 centimeters using the positive sign. So good check. The most important part is, though, that the dA is going to come out in front of that K hat, and you're going to get K hat dot rho hat. And what's K hat dot rho hat?
Zero.
Yes, because rho hat, remember, that's part of the reason why I wrote it with I and J, so you'd see that it's purely in the XY plane. K hat's clearly perpendicular to that. So yeah, K hat dot rho hat is 0. And that's what we wanted. I told you the left-hand side should always be electric field times area, or multiple terms with the electric field times area, or 0. That's the only choices. Now I've got to do, that was the top. Oops. That was the top. Now I got to do the bottom. The bottom is going to be, again, E of Z, but in this case, it's in the negative K hat direction. So I'll put a negative there, and then that's dotted with negative dA K hat. But as luck would have it, it turns out that negative times a negative is a positive. So I end up getting 2 E of Z times A. One for the top, one for the bottom. Now my left-hand side's done. Does that make sense to everyone? Any questions? All right, let me make sure I'm seeing my chat. Yeah, it doesn't look like anybody chat anything. I forgot to put that up earlier. Okay, so the right-hand side is where you can sometimes get the more difficult part. In this case, it should be pretty straightforward. Can anybody tell me, if I tell you, for instance, that the charge per unit area is sigma, and then I tell you that the area of the top of this can, and therefore also the middle section of the can, and also the bottom section of the can, I tell you that's A. Can anybody tell me how much charge would be enclosed in that cylinder?
Sigma A.
Sigma A, exactly. So we're just going to put sigma A over epsilon naught, and the right-hand side's done. Okay. So our final step is to set the left-hand side equal to the right-hand side, and then attempt to extract the electric field. So I get 2 E of Z times A is equal to sigma A over epsilon naught. Now I'm going to make use of my original hypothesis, and I'm going to say that the electric field is equal to sigma over 2 epsilon naught K hat for Z greater than 0. And it's going to be negative sigma over 2 epsilon naught K hat for Z less than 0. And I now have the electric field everywhere for this. Obviously, if you get too far away from a finite electric field, or excuse me, a finite charge distribution, then all bets are off. But right now, it looks like an electric field for an infinitely large plane charge is going to be independent of the distance, which is why they put those diffracting plates on top of fluorescent lights in some stores. The fluorescent light does a good job because it's a long tube, and that long tube, like we showed in chapter 21, has an electric field strength that falls off like 1 over r square, like 1 over r, whereas a light bulb, which acts like a small sphere, has an electric field that falls off like 1 over r squared. So if I go 1 meter away, it's a certain brightness, but if I go 2 meters away, which is just a mere 6 feet, it's actually 4 times darker. If I do the same thing with an infinitely long tube of light, then it'll be a certain brightness at 1 meter, and at 2 meters is only going to be half as bright. With this one, it should actually make it no change whatsoever. So when you put those plates that are for sort of spreading the light evenly as if it's coming off of a plane, then you get the whole room feeling fairly bright with little or no darkening as you get closer and closer to the floor. Now, if we were to actually graph this, you can see there's a ginormous discontinuity. It's actually a neat little thing, and it happens to be a fundamental physics fact. I'll show it to you now. So this would be our distance z, say, and this would be our electric field here, say. What I'm going to do is I'll say this is sigma over 2 epsilon naught, and for z greater than 0, that's it. There's a hole there though. And then if I come down here, this is going to be negative sigma over 2 epsilon naught, and it's going to go forever this way again with an open hole. That discontinuity there from here to here is actually sigma over epsilon naught, and it turns out that electric fields, the component perpendicular to a surface, whenever an electric field penetrates from one area to another, the component of the electric field perpendicular to the surface is continuous if and only if there's no surface charge. If there's a surface charge, it's going to be discontinuous, and the amount it's going to be discontinuous by is exactly sigma over epsilon naught, and that's what we just found. So if you subtracted sigma over 2 epsilon naught minus negative sigma over 2 epsilon naught, you get sigma over epsilon naught. So that's one thing that's kind of important. Another thing that's kind of important is if I were to take 2 planes, let's say this is an infinite plane, its charge is negative, and it has a exact same charge as the positive one did, only it's negative. And then I put right next to it another infinitely large plane that has a total charge that's positive. Okay. Between the two, now just think about just between the two, which way will the electric field point due to just the positive plate? Between the plates, which way is it going to point? To the right or to the left? Remember, electric field always points the direction that a positive charge wants to go. So if I stuck a positive charge between those plates and ignored the negative one and pretended the positive charge is ignoring the negative one, which direction would the electron wish to go?
To the left.
It's positive, and the left one is positive, so it wants to run away from that.
Oh,
So
right.
that would, you might have misunderstood, but that would actually cause it to go to the right. Now, forget about the red plate for a second, but still put a positive charge between the two and ask yourself, which direction would the positive charge want to go if only that negative plate was there? Anyone? Don't feel bad about being wrong. It helps everybody gets it wrong all the time. Remember, like charges repel and unlike charges attract. So I'm asking you, I want to put a positive charge to the left-hand side of a negative plate. Which way is that positive charge going to want to move?
Right.
Exactly. So both of those actually add up. And in fact, between the plates, the electric field becomes sigma over epsilon naught. That's going to come in handy when we do capacitors. What about if I put a positive charge to the right of both of them? What's the red plate going to cause? So right here, a positive is there. Just in terms of the positive plate, which way is a positive charge going to want to go?
To the right?
Yep. What about a positive charge over here, or positive charge over here, but this time just due to the negative plate?
To the left?
Exactly. So out here you get E equals 0. And if you do the other side, you'll find the same thing. The positive charge due to the positive plate will want to go that way, and the positive charge due to the negative plate will want to go that way. So you in fact get E equals 0 out here as well. So that's the origins of a parallel plate capacitor, which we can use to store energy. It's not unlike a battery, except that when you do a battery can only do a finite number of charges, and they do so very slowly. So let me quickly go through a Gauss's law problem for that problem we did in chapter 21. Okay. Remember that god awful integral problem we did in chapter 21, where we integrated an infinite line of charge? That's what we're doing now. So here's my infinite line of charge. It's an infinitely thin, infinitely long wire. So it's really just a one-dimensional construct, if you will. Goes on forever. Goes on forever. And of course, the y-axis goes on forever and the x-axis goes on forever. And even though it's along the x-axis, I'm going to say out here at this distance right here, in cylindrical coordinates, I was saying that variable would be called rho. So I'll just use rho this time. Okay. Now, this is uniformly charged again, and I want to calculate the electric field everywhere. I know that since it's infinitely long, I expect the electric field to point directly away from the y-axis no matter where you are. So if I'm out here on top of my iPad 2 inches above it, I expect the electric field to point straight up perpendicular to my iPad at me. If I'm over here where the rho is, it's going to point to the right. If I'm over here where this dot is, it's going to point to the left. If I'm behind, it's going to point in. So you can see that it has that cylindrical coordinate style to it. So what I'm going to do is I'm going to create a Gaussian surface, the radius of which is rho, and I'm thinking this wire is infinitesimally thin, so that I'm not even taking into account its dimensions, but I'm taking a small section, if you will, of the actual length, and that small section is going to be a length L. So this length right here is L. And what we know is that the charge per unit length is lambda. Okay. So my dA for the top, first off, my electric field, I suspect my electric field will only depend on the distance rho, and it's going to point in the rho hat direction. That's my hypothesis. My dA for the top is going to be dA k hat. My dA for the bottom is going to be negative dA k hat. And my dA for the soup label is going to be dA rho hat. Left-hand side of Gauss's law the closed integral E dot dA is going to be the integral of E of rho hat dotted with dA k hat top plus the integral of E of rho hat dotted with dA rho hat plus, that's over the soup label, plus the integral over the bottom of E of rho hat dotted with negative dA k hat. Can anybody tell me if any of these terms are zero? Do you see this rho hat dot k hat is going to force it to be zero? And this one too. So all we're going to have left is, in fact, E of rho times the area, and that's the area of that whole soup label, which is 2 pi rho times L. Now, if the charge per unit length is in fact rho, or excuse me, is in fact lambda, and I have a length L, how much charge is enclosed? The charge per unit length, which has units of coulombs per meter and is a constant, is lambda. I have a length L, so how much charge should be enclosed in that Gaussian soup can?
Lambda times L.
Lambda times L, very good. So now I set left-hand side equal to right-hand side, and I get E of rho times 2 pi rho L is equal to lambda L over epsilon naught. And lo and behold, we've gotten exactly what we got from that long, awful integral, making use of our hypothesis, of course. We've gotten that the electric field is in fact equal to lambda over 2 pi epsilon naught rho, where before we used R or X, now we're using rho, and it points in the rho hat direction. Okay, so now you've seen how much easier it is to do Gauss's law than it is to do Coulomb's law. Look how short that was. Okay, obviously we ran over by about a minute. So of course everybody's free to go. I will wait for the last person to leave in case you have any questions. And this should be posted either tonight or first thing tomorrow. Have a good evening. Thanks for coming, everybody. Looks like everybody's gone. James, did you have a question, sir? Anything I can help you with? All right, he might already be logged out. Well, have a good evening, everybody. Thanks for coming to Physics 242, and bye-bye.